All right, there are some people here who are new. Welcome to you, to the great ranks of Hamden. If you have as much fun out of it as I have in the last 45 years, nearly 46 years, well may you roll your eyes, young Jim, but you're pretty getting on a bit of yourself. If you do that, then you'll be in good shape. I have to say, Peter, I started talking at this branch in the mid-1970s, and this is the first time that I've arrived for a talk that Jumbo has not been at the front door to greet me. And that's a nostalgic thought. He was part of this branch. Some of you won't know who I'm talking about. Okay, ask around. And I finally left this last year. Now, some of you are looking, some of you don't know who I am. I'm a physicist. Cringe. One of those brainy dudes. No, it's all right. I'm retired, so I'm not as brainy as I was once. I'm semi-retired, which means I'm busier than ever. I work in the physics department at the University of Auckland. And what I've decided to talk about tonight is questions that people ask me. Because of my exalted position, people phone me up and they ask me questions about radio and Morse. I write the Morseman column in Break-In, if you don't know about that. And they ask me a whole lot of other questions as well about general scientific topics. And I'm going to address 3 or 4 of those tonight because I'm sure they're questions that some of you have thought about before. This has got nothing to do with the forward discrete Fourier transform or the reverse transform so you can breathe and sigh of relief. This is merely transparency that I can check everything works without giving away any guts. So, here we go. Here's a question. A lot of people, I get a question about once a week. Is the sea level rising? Are we going to lose our batch here? If the Earth gets warmer, 2 things will happen because of this. The oceans will get warmer and water expands. Thermal coefficient of expansion is water is about 2 times 10 to the minus 4 thingamies per cubic thingamy. And that will cause the oceans to rise because the water will expand in volume. Also, it may melt polar ice caps. Only on land. Now, many of you will have observed as you sit there at an evening with your glass of scotch with the iceberg floating in it, and if you observe carefully, which is difficult after a while, as the iceberg melts away, the level of scotch does not change because of the theorem of who? Archimedes, something that modern school children are not taught about. But thank you, Alan, for that. Yes, it wasn't the principle of hypotenuse. If you don't believe this, and a lot of people don't, they have to try it. You see, melt an iceberg in water and see that it doesn't change. There are other nasty effects too, which I've put down here. The current circulations may alter, particularly in the northern hemisphere. There's a thing called the pump system, which pulls down warm water up by Iceland. This is what keeps the Gulf Stream going, and warms Europe. Europe is about 3 to 5 degrees warmer than it would be if the Gulf Stream was not there. But the oceans also have a major effect on climate, and we know that in the last 40 years, here's some figures from Levitas, who was an iconic figure in ocean science. The upper 300 metres of the oceans have gone up by 1/3 of a degree C, and the upper 3,000 metres have warmed by 0.061 degrees C. And he did this by looking at a very big database of all the observations that ships take that he can get it. And this by itself translates to a level rise of 5 to 15 centimetres. So in that time, 40 years, he reckons the sea's gone up by 5 to 15 centimetres. It's a difficult calculation too. It's hard to find out what the average temperature of the ocean is. This is a picture of the temperature distribution, false colour here. High colour is purple, low temperature is green. Around New Zealand on a standard summer New Zealand day, it's at about 2002. This comes from the NIWA website. So you can see it would be pretty hard to take a whole lot of readings and stroke analysis. This all comes from satellites. We get about 8 pictures like that from satellites per day. So we'll look at some other effects. It also varies. This is the sea surface temperature over the globe. It varies greatly as well. -1 degree down here. -1? How can it be -1 degrees?
Salty water.
Salty water, exactly. Salt water does not freeze at 0. It freezes a little bit lower down. Going up to about 29 degrees. So these are the average temperatures, and you can see that we're in a fairly temperate spot down here. So it's quite a problem to determine what the temperature distribution is and how it varies as time goes by. Well, here's something about melting oceans. We know, or we suspect, that in the last 100 years we've gained about half a degree Celsius. That's not very much, but there's evidence of this rate rising. The North Pole floats on the Arctic Ocean. People ask if the North Pole ice melts, will that raise the oceans? No, because they're like icebergs floating in whiskey. Nothing will happen. There are two big land masses, however, covered with ice. One is Antarctica, and this is enormous. It has 90% of the world's ice and 70% of its fresh water. And you probably know that grandiose schemes have been put forward to cut hunks of ice from the Antarctic and drag them with ships to impoverished parts of the world so they can have drinking water. Well, we're not up to there yet, but it's a possibility. Okay, it's about 7,000 feet thick, and if all this melted, the sea level rise would rise about 61 metres or 200 feet, which is quite a long way. Fortunately, this is most unlikely to happen because the average temperature is around minus 37 degrees C, so that's probably not going to happen, at least for another 4 or 5 centuries. It's a bit hard, so we're not going to have a problem, and our grandchildren are not going to be a problem. So it's okay. We can still burn coal fires. But Greenland, some authorities think, is the major problem. Now, there's disagreement about this. Some people think it's just Antarctic that may be a problem. But Greenland, if all the ice covers Greenland melts, Greenland has got an area of 2.1 times 10 to the 6th square kilometres, and 82% of that is covered with ice. It's also thousands of feet thick, and this would give a sea level rise of about 20 feet or 7 metres if it all melted. And some people think that's more possible. But again, we're talking of time scale minimum of century, 2 centuries, something like that. And this occurs because Greenland is close to the equator and the temperatures there are high, so the ice is more likely to melt. But really, nobody has any idea how quickly these processes will go. We can take amazing videos now using satellite technology. This is one looking at the Arctic sea ice concentration. What we're going to see is a video of what the Arctic ice cap looks like between 1979 and 2003. So we're going to get a lot of shots. Yes, of course. Let's pull this out. And so there's the northern polar ice cap. See how it changes. Can you convince yourself that on the average the white area is getting lower? We'll play that again. This is the sort of picture that the weather scientists attempt to use to determine what the ice is going to do. It varies quite a lot. Yes, it is amazing.
Is that Greenland sticking out to the right?
Yes. The white stuff, yeah. The white land is Greenland, yes.
It doesn't change much.
No, Greenland doesn't change much. No, just as much. We don't want that to change. Alright, let's get rid of that one. We can also attempt to find the temperature variation and display it in false colour. This is from 1981 to 2003. This is brought out by the same people. Again, we'll tie this one and make it a bit bigger. Same start, but now we see colour. Blue is cold, orange is hot. So this is an infrared map of temperature distribution for the years 94, 95, 96, 96, 97, 97, 98. See how variable it is. Here's another reason why it's so difficult to make any long-term prediction in climates, because things fluctuate so much. Let's just play that one more time. So here the world spins around, yes, and that is Greenland up there. And it's changing its temperature a bit, but you can see there's big temperature changes in here. It's not at all clear what's actually going on. Greenland sometimes gets a lot colder.
Why is it called Greenland? It was mostly white.
Anybody know that?
It was warm up until about 1000 AD.
Probably probably a bit later than that, Henry. Yes, it was warmer. It was settled by the Vikings. The Vikings attempted to establish dairy herds there because they liked drinking milk and eating cows. And it wasn't actually a Greenland, but they called it a Greenland to encourage more people to come and colonise it. But it certainly wasn't covered with ice the way it was now. Well, we'll have a look at some historical pictures of, we won't have a look at temperature, we'll do something else. What's the sea level done on, what's the geological timescale? Well, going back into the past, this graph is the wrong way round. This is millions of years ago. This is the present, north, and this is 542, which just happens to be where the graph stops, I think. So this is about 500 million years of records of the sea level. We'll talk about how they deduce this in a minute. There are two separate graphs there by different people. Hallam et al. Published this in a scientific paper, and I don't know where the Exxon sea level curve came from, because I actually stole this one off the web. So what does it tell us? These letters along here refer to different geological epochs, and you can see here we are here, and we're referencing sea levels to 0 here. So these are levels referenced to the current time. In the last glacial episode, now I'm going to expand that bit in a minute. You can see that 100 million years ago, the sea was 250 feet higher than it is now. But then it went right down, and here it's actually about minus 15, and then it goes up, and one of these curves is a big peak here, about 400, the other one's got a peak somewhat later, about 280. How do they deduce these? Well, first of all, we're all familiar that this probably makes sense, because you can climb quite high mountains and you can find fossilised shells, which are far too high for the Maoris to have left there after eating them. And they've definitely, yes, they've definitely been deposited there when this part of the world was under sea, you see. So, well, there was a land bridge between Australia and New Zealand, and there were various land bridges over other parts, and all this comes from geology. You can date using radiometric methods, and you can follow strata at different levels of the earth. This technology is about, well, they've been doing it for about 50 years. And as you can see, there are wide disagreements, except that we have general agreement on what happened. What happened here, this was the second to last glacial episode, when the Earth enters an ice age. A lot of ice accumulated, and that water came from the oceans, and the sea level dropped. And then the ice melted again, and the sea level went up. And now it's melted again, and it's down there. So, long term, we're at a fairly low level, okay? And this is a historical trend. Now, this graph is plotted the right way around. This is thousands of years ago. This is the blow-up of the far right-hand, left-hand corner of the previous graph. 24,000 years ago up to the present. And here we have height, minus 140, up to north here. So, when the last glacial maximum occurred, that was when the ice cover in the last ice age was at its highest. That's actually not long ago, is it really? 22,000 years ago? That's not millions of years ago. This is pretty recent. This sea was about 130 feet lower than it is today. Meters. Thank you, Simon. I'll use Fahrenheit and Celsius too, and I'll use, never mind. Aberdeen in Scotland, this record is going from 1862 up to 1996, shown here. And there are two graphs, there are maxima and minima, and there's a mean trend in the middle. But we can see from that, and this scale here is in millimetres. All these scales are different because they've been done by different people. So I guess what you can see that the sea level's apparently gone up at Aberdeen about 5 centimetres in 130 years. If you look at the same sort of record from Stockholm, and it's in a different form because it was done by different people, then the sea level has apparently dropped 40 centimetres in 130 years. Now this seems rather odd because it's the same sea. let's look at the South Pacific. If we look at Nauru, Nauru hasn't done very much at all. Turns out that Nauru, these are in the southern hemisphere, Nauru is particularly affected by El Nino events. There are cyclical variations here, but there's not much of a trend there. This is at Montevideo, there's not much of a trend here. And this is at Tuvalu, there's three graphs here. This is the mean level, this is the maximum level for a period, and this is the minimum level for a period. And you can see that there isn't very much here. You may note that, well, you may know that some years ago there was a lot of angst in the papers about islands like Tuvalu, who they feared were going to be engulfed by the rising sea levels. This doesn't show on graphs like this at all, but there are two other effects that they now believe are responsible for that. One is that the weather is getting more extreme, apparently, and there seems to be evidence of that. The second one is there's quite a lot of erosion at Tuvalu going on at the moment. I'm not sure why. As the ice melts, the ice is very heavy. There was a lot of ice in Alaska, as you'd expect. The ice has slowed off Alaska. Alaska is saying, and it's breathing out, and this lessened weight is causing the land mass to come up slightly. And while it's doing that, it's pushing down by a complicated geological process the land. Some of these apparent rises are caused by things like the water tables are going down, groundwater is being exhausted, and natural gas is being pumped out. But anyway, you can see why the Americans are a bit alarmed about this, and I think if you look at a picture of London, I don't have one, you see something a bit in the middle like that as well. And London is taking this very seriously, as you probably know. They're putting large sluice gates at the start of the River Thames. So it's the relative movement that's important. If you take, now this is a very recent graph, what these people did was to take 23 annual tide gauge records and they tried to correct them for the relative movement of the land masses, which they deduced by geological means. So here are the 23 records, all plotted with this mucky green and brown stuff here, and here's the average of them all here. And here we go from 1880, the level is 0 up to about a bit over 2000, and the level is 20 centimetres. So this graph is saying from 1880 to 2000 and something, then the seas there's been a true rise in sea level, quite independent of what the land is doing by 0.2 of a metre. Just recently, we've been able to make similar observations with the topics Poseidon satellites. So I won't go into the technology of that, but with these satellites, you can accurately measure distances to with an accuracy of millimetres. And since they know the orbits very accurately, this gives you a means of calculating what the true surface of the ocean is doing. And finally, the bottom line. Paper published this year. From 1870 to 2004, the seas rose by 20 centimetres. In this century, the rate of sea level rise is about 1.7 plus 1.3, say 2 millimetres per year. Every year the sea's going up by about 2 millimetres. Actually, in parts of the earth, it's going out a millimetre a year. Places like New York, as the land is sinking, apparently, but there's a true rise. But this rise is getting faster. There's an acceleration of 0.013 plus or minus in the 20th century, and they extrapolate and say that if this continues, then the 1990 to 2100 rise will be between 28 to 34 centimetres, maybe a third of a metre. And that seems to be as accurate as anybody's prepared to predict at the moment. Now, if you search, I don't know if you've ever Googled on sea rise, but if you do, you will find literally thousands of websites, fascinating websites. All the meteorological places in different countries put them out. NASA has got a great website, NIWA's got a website, and you can get more information than you wanted, that you can shake a stick at. Okay. So last of that topic. Interrupt me any time with questions or when you all fall asleep. If you fall asleep, put your hand up and I'll stop. That deals with my first topic.
Garry, to that's sort of given an idea that the global warming is coming on at a fairly constant rate. But we've actually got all the methane now that is being released from peat bogs and trees.
Well, yeah, but just because we know about it doesn't mean that it's happening any faster. Well, and actually this was known 30 years ago, but nobody wanted to know.
Yeah, but so the methane hydrates and things, the ocean's getting warmer. They're measuring plumes coming off on the old sonar multi-beam tracers now.
That's right, and they now know that they've seen methane plumes over the forests in South America for 3 decades. Because the professor of geophysics where I worked, Jeff Austin, was involved in an international experiment 30 years ago where they measured the inflow and outflow of gases above the Amazonian rainforest, and they showed quite conclusively that the trees suck in carbon dioxide during the day and they pump carbon out in the form of methane at night. But they wanted to publish this in Nature, and the editor said, will this paper support global warming? And they said, no, it won't. It will either support or not. It's completely neutral, and the paper was refused publication.